Hello, a great welcome to the series on Abaqus. Myself Jarajan P. This is tutorial number 13 and provides the geotechnical capacity analysis of a single pipe. So let us first go through the problem statement. As shown in the figure, we shall consider a soil domain of radius 15 meters and height 25 meters for the capacity analysis. The pipe that will be investigated is of 60-meter long and a diameter of 0.6 meters. Please remember that the GWT, that's the groundwater table, is below the zone of pile influence. Hence, the groundwater presence will not be taken up in this analysis. Please remember that when the groundwater table is within the zone of influence, we shall perform the analysis based on whether a long-term or a short-term response is required. Anyway, such topics will be taken up in the coming tutorials. So coming to this problem, we have two materials. One is soil and the other is concrete. And the soil has got a mass density of 1.8 ton per meter cube and a Poisson's ratio of 0.28. The E value, that's the Young's modulus of elasticity in kPa, is at 10,000. And the plasticity behavior of the soil will be modeled using the Mohr-Coulomb criteria. The friction angle will be taken as 32 degrees, dilation angle will be 1 degrees, and the coefficient will be 10 kN per meter square with an associated plastic strain of 0%. And the pile to soil interface that will be used in the penalty definition of the contact interaction will be 0.42. Obviously, this is calculated using the phi value. Now, the concrete considered for the pile has a mass density of 2.5 ton per meter cube. The E value used is 2.5 ton to 7 kPa and the Poisson's ratio is 0.2. So let us proceed to Abaqus. So let us start with the part module. So here we have two parts, one is the soil and the other one is the pile. So let us proceed for creating the part for the soil. Please remember that the modeling space here chosen is axisymmetric because it will reduce our computation time and make very less requirement for the computation efforts. So let us keep the approximate size as 50. So draw a rectangle and the dimension of the soil rectangle is 15 meters by 25 meters. So 15 comma 25. Yes, okay. So you can see that yes, we have sketched it properly. Done. So this means that the part for the soil is ready. We shall proceed with the partitioning after the creation of the second part, that is a pile. So let us proceed with creating the second part, pile. The modeling space will be the same. So continue. So let us draw a rectangle. And the radius of the pile, that is 0.3 meters. And its height is, or the length of the pile is 16 meters. So you can see that yes, the part for the pile is also made. Okay, so now let us go back to the soil and do some partitioning. So first of all, the basic purpose of partitioning here is, obviously we know that the pile need to be embedded into the soil. So we shall cut from this soil column or the soil element a portion that is relevant to the pile. And also from the point of view of the meshing also, we'll do some additional partitioning. So let us first do the partitioning in the vertical direction. So we shall go to, okay, we shall go to this create partition, the face, sketch. And now let us make use of the offset curves here. Okay, first of all, cross this line, okay, so done. And now the offset distance. So obviously I want to draw a line at 60 meter that corresponds to the base of my pile, so 16 meters. Okay, now we have to see that whether the offset is made in the right direction. Yes, it's a red line that is indicated, that is acceptable to us. Okay, so done, fine. So now let us also make a vertical line here that corresponds to the pile soil interface. Obviously that we have to be offset at a distance of 0.3 meters. So offset. So select this line, right, and done. Now we have to see the offset, that's 0.3 meters. Okay, fine. Now whether this offset direction is acceptable to us? Yes, it is acceptable. Okay. So we have drawn a vertical line also. Now I want to draw one more vertical line where I want to use a smaller mesh. For example, right from the center up to 1.5 meters, I want to use some kind of a finer meshing. So for that, let me also draw one more line, one more offset. So let me select this line once again. So done. And this time I want to offset it at a distance of 1.5 meters. And this is for the meshing purpose. Okay. And the direction is acceptable to me. It is indicated by that red line. So this is okay. So this means that our partitioning for the pile, that's for the soil, that's complete. So done. So you can see that yes, we have the partitioning. See this line, this indicates the pile element, the soil element which has to be deleted. So let us delete this soil element because we want to accommodate the pile in this space. So take this remove space, okay, and select the face. Okay, right, done. Yes, okay, fine. So you can say that the partitioning of our soil is complete. We don't require any kind of a partitioning for the pile. So this means that, so look into this particular part, you can say that yes, we require some kind of a dense meshing in this area, which is very closer to the pile, and we can use a little bit of a relaxed meshing in the other areas. So now let us go straight to the property. The property, we need to define two properties, one for the soil and the other for the concrete. So let us start defining the material. So this is the soil. So this is soil, and in the general we'll define the mass density as 1.8. Remember, in this tutorial we will follow consistently kilonewton and meters. So accordingly we have to feed the mass density in ton per meter cube, that is 1.8 ton per meter cube. So now go to this mechanical, go for the elastic property definition, choose the modulus of elasticity of the soil, that is 10,000. So I think it's okay, 10,000 kPa, because we need to be very careful while providing the properties to the Abaqus model. Any change is likely to affect the final response. So please double check all the properties. Okay, and now the Poisson's ratio. The Poisson's ratio will input it as 0.28. 0.28. Okay, so my elastic properties is also over. Now let us go in defining the plasticity. And the plasticity, as discussed, will be described in terms of the Coulomb plasticity model. So here we have to define the plasticity in terms of the friction angle as well as the cohesion. So enter the friction angle. The friction angle is equal to 32 degrees, 32 degrees, and a dilation angle of 1 degrees. And I'll go back to the cohesion. The cohesion enter a value of 10 kilonewton per meter square, and the associated plastic strain level that you can enter as 0. This means that we have defined the density, elasticity, as well as the Coulomb plasticity parameters for the soil. So the definition of the soil property is complete. Now let us proceed for defining the property of concrete, that is the material for our pile. So go for a material, that is, let me call it as pile. So pile. So obviously we'll go for the density first. So here for the pile the density may not be required, but let us just enter it. That is not a big deal at all. But remember, the mass density will be required for other calculations where the dynamic analysis, the initial effects are to be taken care of. Anyway, we are inputting all the required parameters. So mass density 2.5. Now let us go and define the elastic properties. Elasticity and the Young's modulus. The Young's modulus will be 2.5 into, okay, so we can have it as a 2.5 E7 kPa. The Poisson's ratio will keep it as a 0.2. So this means the property definition is complete for us. Now let us start to defining the sections. So we'll define two sections, one for the soil. Select the material as the soil. Okay. Define one more section, that is for the pile. So select the property as the pile. Okay. And now let us start assigning these sections. So this is our part that is representing the entire soil. Select it, done. Okay. Now this is soil, so select the section soil. So that's okay, fine. Now let us assign the section for the pile also. So select the pile, okay, done. So let us select section pile. Okay, so this is that yes, we have completed the property also. We can go straight to the assembly. Okay, and in the assembly we shall start selecting doing the independent, because it's a very simple model. We need not to measure one part, we can straight away start measuring directly on the instance itself. So let us select these two together. Okay, so that is okay for us. Okay, fine. Now we need to shift the pile. So now you can see that is the top is somewhere here. We need to bring out to this point. So let us translate the pile instance. So translate. Okay. So select the instance to translate. Okay, that's okay for us. Done. Now we have to select 2 points. One is a start point. Okay, we have got one edge over here. So let me select this as my start point. And the end point will be this point. Okay, fine. Yes, the position is acceptable to me. Okay. So this means that yes, we have placed our pile, okay, properly inside the assembly. Now you can also go back here and you can use the color coding based on the parts. Yes, so this is more convenient for you. So you can see that yes, now the entire soil model it is being now indicated in the gray, whereas here we have got some other color for the pile. So this means that our assembly is also complete. So now we can proceed straight away to, it's a very simple model basically. So we can go straight to the step, and here please remember, though this is a very simple problem, we have to be very careful because this is not a model involving standard material like the steel or aluminum. It is involving the soil. So we have to define the the steps very sequentially in a better way. And also here there is one more thing that we need to ensure, that is before Abaqus starts the analysis, the entire model is in equilibrium. Okay, so let us start proceeding with the step creation. Here we have two steps. One step will be used for applying the sulfate of the soil, which is done through the geostatic function or the geostatic step, and the second will be used in gradually applying or loading the pile through a displacement option. Okay, so let us start proceeding for the uh, step. So I'll call it as a step for easy identification sulfate, and here procedure type, you should choose the geostatic, because the geostatic procedure is a standard procedure that you can directly use in our geotechnical analysis. So that is continue. Okay, continue. Now let us start defining the parameters for the geostatic. Normally the analysis, unless and until there is any specific complication, the analysis should not take any time at all. A single step itself it will provide you the answer. So try to keep all these parameters as default itself here. So for example, for the geostatic, keep the NL geometry option as off, and the incrementation you can keep it as automatic. And as you can see that the increment size everything is kept as 1 and 1. You need not to change it. And as this is a problem that involves the friction component also, you can, for example, to make the computation much more efficient, you can keep this as a matrix storage as unsymmetric. That's okay. So this means that we have defined one step for the applying the sulfate of the soil. Now let us define one more step. That is a step I will call it as a for pile. For this is for applying the pile displacement, and that has to be placed after this geostatic step. And remember here the procedure type will be static general. Okay, continue. And in this case you can just go on. For example, okay, our time period will be 1, and if you want, okay, I have kept, for example, here off also. You can keep it on and see whether there is going to be any difference. And in order to ensure that yes, there is a convergence, so I made the automatic stabilization on. And then coming to the incrementation, let me keep the number of increments a little bit larger. It's a very small model, so it should not create any problem for us. In spite of that, let us keep, this at 0.05. So, and here the option will keep it as a unsymmetric. So that is okay. So now we have defined the two steps. One is the geostatic step, and the other step is meant for applying the displacement loading to the pile. Now let us proceed directly to the interaction. So first of all, let us define the interaction property. So interaction property 1, we call it as the contact. So continue. So here we shall define the interaction property in the tangential as well as the normal direction. For the mechanical, go to the tangential, and we shall use a penalty function and provide a friction angle of 0.42. Okay, please remember that this is calculated based on the phi value. Okay, now so the tangential behavior is over. So now let us proceed for the normal behavior. The normal behavior will choose the hard contact. So that's okay. So this contact property we defined just now will be used in modeling the interface between the pile and the soil in the length direction. Now for the bottom, we'll use a constraint option to provide the interaction. So let's start defining the interaction. Please remember that for the 2D axisymmetric model, this automatic facility of finding the contact pairs will not be available. So we have to define it, the contact pairs individually. Okay, though this may take time, this is a simple model, so we have got only one surface to surface pair here. So the create interaction, so let me call it as ILT1. ILT1, so I will define it in the initial time step. Okay, I will call it as a surface to surface contact standard. Okay, obviously it will ask you which is the master surface and which is the, remember that we are going to model the interaction between the pile and the soil in the longitudinal direction. So let us first select the master surface. We'll choose the pile surface as the master. So we can select this surface. So what we can do is that go over here, and here you can see that yes. So first of all, for the master, we can just keep the pile only on. So let us remove the soil from here. Okay, fine. So let us create this surface. Okay, fine. So this is the master pile surface. So this is done. Now we have to select the slave surface also. Before selecting the slave, let us keep this on. Okay, and let us remove the pile. Remove the pile. Okay, fine. So let us define this as surface again. So select, this is my source surface. Okay, done. You can see that yes, the master and the slave surface are indicating the two colors, cyan and red, and we are using a surface to surface interaction. And remember that you have chosen the right interaction property defined just ago. So that's interaction property 1. So this is okay for us. So we have defined the interaction between the pile and the soil in the along the length direction. Now we need to define the interaction between the pile bottom and the soil, and this will be done through the constraint option available here. So let us do one thing, define a constraint here. So constraint 1, and we will call this as a tie constraint. Okay, tie constraint, continue, and we have to choose which is the master and which is the so just we'll go over here and we'll choose now the pile. Okay, so we'll choose the pile here. Pile will add, and let us remove the soil from here. So remove the soil. Okay, so this is my surface. So this is my fine. So I select the pile base. Done. Now we need to select the slave surface, that is essentially the soil. So go over here again, So include all the components here. Okay, so let's add here, and now let us remove the pile from here. Okay, so now you can choose the slave surface. Select the surface. Done. Okay. Now here you can see that yes, the master and the slave surface is being specifically highlighted over here. So you can see that yes, we have established what we call as a tight constraint over here between the soil and the pile bottom. So this means that the interaction definition is complete. So before going to the other module, what we need to do is that we need to define a reference point over the top, because rather than applying the uniform displacement over this length, we would like to apply it through a control point. Okay, so let's define first of all a reference point, and we want to keep a reference point that is just at the midpoint of this pile. Obviously that must be a point 0.15 comma, and this is 25. Okay, you can see that yes, this the reference point is automatically created, that is rp1. Okay, so that's okay. So the reference point is complete. Now let's tie this reference point to the pile section through another constraint. So I will create another constraint too, and here I will use a multi-point constraint option. Continue. Now select the MPC control point. This is my rp1 is my control point. Now I have to select the region for the slave nodes. So this is the region for the slave node. Okay, so done. And here we will use the tie option again here. Okay, so you can see that yes, we have established a reference point for the application of the displacement. So this means that we have completed all our activities in the interaction module. Now we are ready to go to the loads. And the loads module, we have two assignments. One is the creation of the boundary conditions, and the second one is application of loads. So let us first of all proceed for the boundary conditions. So create a boundary condition as such. So first we'll create a boundary condition for this free edge. For this free edge, that means I'll call it as x free, okay, and that will be placed in the initial displacement. Continue, and select this face, okay, where we want to apply the boundary condition. Done. And here I want to restrain my u1 displacement. Okay, so okay, fine. Now let us define the boundary condition along this axis, which essentially is the boundary condition corresponds to the axis of symmetry. So define one more BC. BC you can call it as, this is X symmetry, okay, and we'll use the standard type available symmetric or anti-symmetric condition here. So continue, and now we need to select the regions for this boundary condition. So you can select this edge and also one more at this. Okay, so done. So here this x-axis, so x symmetry, so that's okay. So we have used the boundary condition. Now let's create a boundary condition for the bottom as well. So BC bottom, and we'll use the displacement option and continue, and let us select the edge here. Okay, done. And here we will restrain all the u1, u2 and u3 and ur3. Okay, fine. So we have completed the definition of the boundary condition, but here while applying my load, I want to ensure that there is no u1 displacement for the pile top. So let us also create one more boundary condition for the pile tip. So I will call it as BC pile tip. BC pile tip. I will call it as okay displacement. Okay, fine. And select this part that is corresponds to the pile top. Done. Okay, and I don't want to have any kind of a U1 displacement in this direction, so I'll restrain it. Okay, fine. So that's okay. So this means that we have completed the boundary condition. We can straight away go ahead with the application of the loads. As already detailed in the step module, we have to apply the loads in 2 steps. Okay, so let us proceed for. So create a new load. I'll call it as load self weight. Load self weight. Okay, fine. And let me call it as I will create this load in the step self weight. Okay, fine. And use the type as the gravity here, right? Because I won't apply the self weight to the gravity option here. Continue. Now we have to apply the component here. So let us select the first of all the entire model. Fine. Okay. Done. Now component 2, that will be 9 minus 9.81. Okay, so that is the okay, fine. You can see that yes, the gravity loading is already applied. So now let us proceed for applying the displacement load also, and obviously the displacement load has to be applied through the boundary condition. So here we have to apply one more boundary condition, BC FDN. So or I can call it as BC pile displacement, and this will be applied in the step for the pile displacement and continue. Okay, now we have to select a region for the boundary condition. So I will select directly my RP1 because it is tied to the pile top. Done. Now we have to use the U2. I'll apply a uniform displacement, okay, which has got a maximum value of -1 meters, and that will be gradually applied in the ramp manner. Okay, fine. So that is okay for me. So we have applied a downward load also. Now, so this means that we have completed the self weight. We have also applied the displacement loading to the pile top. Now here one option is left, or one more. We have to define the initial stresses, just like the boundary conditions. For all geotechnical problems, we need to define the initial stress conditions within the soil. Okay, so let us define it. So that is, this you can say that here there is something like a create predefined stress. So you just create one predefined stress. So let us call it as a predefined here stress. Okay, so I will apply this right in the initial and the mechanical or the geostatic stress. Continue. Okay, so now we want to select the regions to select the industrial. Done. And the stress magnitude. Now we have to define the stress magnitude. So at location 1, let me say that we are talking about the base of the soil, that is at the y equal to 0. So we have got a stress of minus 1.8 into 9.81 into 25. So this is the initial stress gamma. This is my total gamma, that is a mass density 9.81, and this is the height, and the vertical position is 0 here, and the stress magnitude at the top will be 0, and the corresponding height, the total height, we know that it is 25, right? So this is 25. So we have defined basically the initial stress. So in the geostatic predefined field, you have to define the stresses at the bottom as minus 1.8 into 9.81 into 25, because 25 is the total height of the soil deposit or the soil model that we considered. And then at the top we have got a zero stress that corresponds to a vertical coordinate of 25. So, and here we have to use the lateral coefficient also, use a lateral coefficient of 0.50 here. Okay, so this completely defines the initial vertical and horizontal stresses. So okay, you can Fine. So you can say that yes. So the stress conditions are also being properly incorporated in order to simulate the initial stress conditions within the soil mass. And please remember, this is an important priority requirement of the any geotechnical analysis. Okay. So now we are ready to go to the mesh module. So as you can see that the completed meshing is shown here. So as already mentioned earlier, you can see that a heavy dense meshing is used in and around the pile, that is for 1.5 meters, and then a meshing, that's a light meshing, is used on the other, away from the pile. So here two things I want to mention. First thing is that here we have used the structural meshing. So you can see that the pile is divided into four parts. Okay, one, two, three. That's the three parts, and the soil portion just below the pile is also divided in the same fashion. And you can see that there is a uniform division in the first 1.5 meters, and thereafter you can see that the mesh spacing is increased. And regarding uh, the logic that is used, you can say that we have used a structured meshing. Okay, fine. And then regarding the element, remember that it's an axisymmetric problem. So we have selected a CAX4 element, that is, it's a 4-node bilinear axis symmetric quadrilateral element. Okay, fine. And here we have unchecked the reduced integration. Okay, so that is all regarding the meshing. Now, having completed the meshing, now we are ready to proceed for the submission of the job. So submit the job. Okay, so let us create the job first. I call it as job 1, or let me call it as a job single file. Okay, and continue. So all the default options are applicable to me. Submit it. So you can see that yes, it is submitted for the analysis, and it's running. Okay, now let us start reviewing the results. So here is shown the variation of S22, that is the vertical stress in the initial time step. So you can just press over here. You can see that you are in the surfeit. You can just press it 0 to 1. So here we find that yes, the stresses they are varying linearly. You can see that the stress is almost zero at the top surface, and it is maximum to minus 37 kilonewton per meter square. This is very well in line with our hand calculations. Now, Abaqus also provide you the facility to see the full model, because if you remember, we have modeled a 2D axisymmetric problem. Now we can also see a full sweep model. For example, if you go to the view, there is a view ODB display options. In the ODB display options, it provides you both the mirror as well as the sweep. So let's go for the sweep. In the sweep, let us apply 0 to 270, because we'll be able to see the full pile. Okay, apply. Okay. So fine. So this is how 3/4 of the model, complete cylindrical model looks like, so that you will be able to see the inside pile also. Now let's quickly see the variation of here the displacement U. So we'll go to U, and we'll have it a U2. That's the vertical displacement. U2, okay, fine. So now let us see how the displacement changes. Okay, so we can go over here. You can see that, look into the pile tip here. You can see that yes, the pile tip is advancing. We zoom it a little bit. Yes, assuming it is coming down, it is coming down. You can say that as it moves, it takes a part of the soil also along with it. So this is how the pile moves as it is pushed down by 1 meter. As you can also see that the pile is also moving down, and at the end it is down by 1 meter. So this is how you can also see a full three-dimensional representation of the soil pile model, though you are modeled in the axisymmetric 2D model. Now we need to go with the extraction of the proper data. Let's see, here we wanted the load as well as the displacement data. Before that, let me remove this. Let me come back to the normal model. In the ODB display option, I'll just disable it. Apply. Okay. So this is okay for me. So I will also go over here. Common options. I'll ask for to give me the exterior edges as well. Apply. Okay. So that's good. and let me take it to the, okay, that's okay for me. Now let us start extracting the important data for us. That is, one is the load displacement data for the pile. So let's extract the required data. So press the create XY data button, and source will be obviously the ODB field output. Continue, and now start selecting which are the forces we want. Actually, the data pertaining to the reaction forces. Okay, which is the reaction forces that will be developed at the pile top. Okay, so you can select the RF2, that's the reaction force in the to y direction, and also choose the displacement, that is the U2. So this will be help you to provide a displacement load plot option. Okay, so let us extract this data first. So these are the variables which we are interested. Select the nodes. Now you would like to select the control point on the top that we created RP1. You can edit the selection here. Okay, and select the node over here. So let us go here. This is my node. Okay, so you can just plot it. So you can see that how the displacement, and so you can see that yes, till the beginning, till the end of the first step, we don't have any kind of a load development, and there is no displacement. And you can see that the displacement gradually increases from 0 to -1. And during this course, you can see that yes, the load on the pile has increased uh, from 0 to 3 into 10 raised to 3 kilonewton. That's 3000 kilonewton. So you can see that in the beginning of this curve, you can see that the pile is very rigid, right? And then it loses its rigidity, or it becomes what we call as a curvilinear over here. So and it goes up to say 1 meter displacement. Okay. So now what we can do is that we can just copy this data. For example, if you edit this, it provides you the variation of the RF with respect to the time. At a time t equal to 1, the RF was 0, and at a time t equal to 2, the RF was minus 3000, approximately minus 3100 kilonewton. You can copy this and then paste it in Excel. Okay, and similarly go back to U1, U2, just to edit it. You can say that yes, edit. You can see that yes, the displacement was almost 0 at the beginning of the step, and then it gradually up to at the end of the second t equal to 2 seconds, you can see that the displacement is -1 meters. Okay, so you can copy these two data and paste in the Excel file. I have already pasted it for saving in the time, and these are the data which we have copied from the Abaqus, and finally we obtain the load displacement curve. So you can see that as is very clear from this plot. So the change in the elongation, or the settlement of the pile is very small in up to say 1000 Newton. That means it is very stiff up to a load level of 1000 kilonewton. From 1000 to 3500 Newton, you can see that yes, the stiffness goes on degrading. Okay, now using the various standard practice available in the literature, you can from this plot you can easily calculate the ultimate load capacity. So the normal procedure is that you draw the two tangents at these two branches, and where it intersects, you take it as the ultimate load. So that is all for this tutorial. We will see for advanced geotechnical tutorials in the coming weeks. And along with that, you can also expect very interesting structural tutorials as well. Till then, bye.